Happy Friday, everyone. I'm glad that you've made it to this video, but before you start to watch the video lesson, make sure that you have already checked your homework from Thursday, because if you have questions, you're getting into that Google Meet later to ask them. Make sure that you've already taken the notes that I asked you to take on page 113 and 114, those key concepts, before you start the video. So if you haven't done that, pause the video, go back, take your notes first, because we're going to start by talking about those properties of equality and properties of congruence. Okay, so I'm just using my document camera, so let me get a little settled here. So in your textbook you had several properties of equality. So these are all properties of equality. Your first four, the addition property, subtraction, multiplication, and division properties of equality, are all just talking about what happens when you're trying to solve an equation. So with that addition property, whenever we need to add something to both sides of an equation, that's what that addition property of equality is talking about. So if we're trying to solve an equation like this, and I have to add 2 to both sides, the fact that I go from 3x minus 2 equals 10 to 3x equals 12 is using the addition property of equality. By the way, for all of the properties of equality, you are welcome to abbreviate them POE. So when we're using this, we're saying we use the addition. Oh, I'm running out of room here, aren't I? The addition POE. So you don't have to write property of equality every time, but I do want that POE because it is different than properties of congruence. I'll show you that in a minute. Same thing when we go to solve this. Our last step is dividing both sides by 3. So we would say that we use the division, because that's what we did to both sides, property of equality. All that property of equality part is saying is that it is a property that we're allowed to do because it's an equation. So I'm adding something to both sides, subtracting something from both sides, dividing, multiplying. Any of those four are all properties of equality, and we're able to do the same thing to both sides. Now with our our reflexive property of equality, it is an equation, but we're saying that something equals itself. So to remember this one, I always ask students, if I asked you the first thing you thought of when I say butterscotch, your reaction is to be like, butterscotch. That might be the first thing you think of. So this reflex is just saying that A equals A, it equals itself. 7 equals 7. AB equals AB, talking about lengths of segments. So the symmetric property is what tells us, and you would have heard these all in Algebra 1, that if I have two things that are equivalent, I'm always allowed to flip them to where I'm saying the opposite one first. So if A equals B, then B equals A. If 3x plus 2 equals 7, then 7 equals 3x plus 2. That's fine, I can switch those. So this is symmetric. You could think about there being like a line of symmetry right here, and those statements would be symmetric about that line. The transitive property is very similar to the law of syllogism that we talked about yesterday, I guess. I'm filming this a day in advance, but yesterday. So that transitive property is what tells us if A equals B and B equals C, then we can cut out that middleman, just like the law of syllogism, and say that A equals C. Our last one, substitution property, if we have stated that something equals something else, then I'm allowed to replace either one of them for the other in any expression. So if I tell you that A equals 7, I'm allowed to replace 7 anywhere where I have A, or vice versa. If there's some reason that I want to replace 7 with A, I could do that as well. So B could replace A, and also A could replace B. Our last one on the next page that you're writing down is our distributive property of equality. Oh, sorry, I didn't mean to say equality. This one is just the distributive property. It doesn't have the equality attached because it doesn't have to do with both sides of the equation. Whenever you're distributing something, we actually don't need an equation involved to distribute A to both B and C. So just an algebra property that we use quite often. I didn't have you write down the properties of congruence because they are all very similar. The only difference is that with properties of a congruence, which you can abbreviate POC, the only difference is that instead of talking about lengths or numbers, we're talking about the actual objects. So one of those kind of picky things that if I'm talking about the reflexive property and I say AB without the line above it, then I would just say AB equals AB, and that would be a property of equality. Or if I said the measure of angle A is equal to the measure of angle A, that would be a property of equality because we're talking about the numbers, the measure of the angles or the measure of the segment. But if we're talking about the segment itself, then these properties are properties of congruence. So if I'm talking about segment AB is congruent to segment AB, I use property of congruence. And you'll notice if you're using it in the problem, there will be a congruent symbol in the problem. So instead of saying property of equality, we'll say a property of congruence. So first, I just wanted to do a few examples of what these might look like and just deciding what property is being used. And you have some like this that you're going to be practicing in your homework. The homework is very short, by the way. I just want to see if we're understanding the different properties, if we can use them, and we will continue using them on Monday. So our first example, we've got if BC equals EF, then EF equals BC. So think about it for a second. If you've got to look back at the properties, look back at the properties. On any of these, if I'm going too fast, pause it, decide for yourself, and then see what I say. Okay, so by now, maybe we've answered. But this is going to be the symmetric property of equality. So that POE part. And because we're using equations and talking about the measures of the segments, that's why we're having a POE. And we've just swapped the sides of the equation. For example 2, if x equals 5 and x plus y equals 12, then we know 5 plus y equals 12. Think about it. This is going to be that substitution property of equality. Because we said that x equaled 5, that means I can replace it in any equation or expression. So I'm just taking the fact that x equals 5 and replacing it in the equation here. So since x plus y equals 12, I can replace the x with the 5, substitution property of equality. For example 3, AB equaling AB. Hopefully that, A equals A, coming back at you, that we're using the reflexive property of equality. And then our last example, if angle ABC is congruent to angle DEF, and angle DEF is congruent to angle HIJ, then angle ABC is congruent to angle HIJ. So a lot going on in this one, but we might notice, just like that law of syllogism, we have that angle DEF repeated, and then we're cutting out that middleman and going straight from angle ABC being congruent to angle HIJ. So this is the transitive. And since we are using congruent symbols and talking about the angles themselves and not the measures, this is a property of congruence. So transitive POC. All right. So what we're going to get into today is mostly using those first 4 solving algebraic equations and using those properties, but we're going to get a little bit into what a proof looks like. So if you were here in class yesterday, go ahead and get out the worksheet that I handed you all yesterday. Fingers crossed that I remembered to hand it to you. If you weren't in class, you can either print it, I put it on the Google Classroom message with this, or you can just go ahead and write the parts that are printed here and pause the video and write that part. It won't take you too long to add that part to it. But this is what we're looking at is a 2-column proof where we've got the steps or what we're saying mathematically, and then on the right side we'll have the reasons for each step. So we're going to look specifically at algebraic proofs today. We will get to geometry proofs. That's the goal, that we get into geometry proofs and try to prove some things that we've already talked about in Unit 1. But for today, we're going to talk algebraic just so that you can see what I'm talking about here. So, our very first step in a proof, first of all, they'll always tell us what we're given and what we're trying to prove. For algebra, it's going to give us an equation and then tell us what x equals, and we are trying to prove that. So for these, we even have all of the steps written in there. We're just coming up with the reasons. Typically, an actual proof is all blank. It doesn't have steps or reasons. Our very first step is always going to be to write the given. So literally, verbatim, whatever they give us, we're going to put as step 1. Our reason for step 1 will be given. Sometimes we're given one statement, sometimes we're given several, but we'll always put in our given first, the reason being given. Now, just like that first example that I was showing, we're going to be asking ourselves, what is happening from this step to this? So we're not trying to solve it ourselves necessarily for this because they already have the steps, but deciding what they actually did from step to step. So we might notice that to go from here to here, they added 1 to both sides to get the 8 and for that 1 to go away. So because they added 1, and sometimes it helps to write it in, but you might be good without that. Because they added 1 to both sides, that means they use the addition property of equality. Added 1 to both sides. Okay. Then from step 2 to step 3, they divided both sides by 4. If it helps you, write it in. If not, that's all right. Divided both sides by 4, so they use the division property of equality. So this is our way of saying, I went from this step to this step, and this is why I was allowed to do that. I went from this step to this step, this is why I was allowed to do that. Okay, let's try another example. So example 2, we've got our given, what we're trying to prove. Remember, our first step is just verbatim the given, and our reason for it is given. From this step to this step, see if you can answer in your head what happened. They subtracted both sides by 3, subtracting that 3, subtracting this side from 3. So they used the subtraction property of equality. And then our last step in an equation, a lot of times our last step is division, but dividing both sides by a -2. So our last step reason is division property of equality. All right, tracking? I hope so. If not, show up in that Google Meet so we can talk about it. So this one's a little different. Our first step is, of course, our given, what they gave us. But that next step, from step 1 to step 2, all they've done is combine this 2 and 6. So this isn't really a formal step, but I just call this combined like terms. So anytime this happens, we've got combined like terms, and you're welcome to just say CLT. That's fine. That doesn't happen too often. We've got combined like terms. From step 2 to step 3, can we tell what happened? They subtracted x from both sides. Okay, so the subtraction property of equality. So it doesn't matter on the ones before, they were trying to get rid of something on the left. Here we're kind of moving something from the right. Doesn't matter, still subtracted both sides by x, so subtraction property of equality. From step 3 to step 4, we subtracted 8 from both sides, so again, subtraction property of equality. And then our last step, again, that division, dividing both sides by 2, property of equality. Okay. Our last example here, the first step, or second step, I guess, is a little different, so I'll do that part with you, and then I do want you to try the rest on your own. So that first step being our given. From step 1 to step 2, we notice that they've multiplied that 4. Okay, so that is our distributive property. Remember, this one is not a property of equality, kind of a picky thing, but not a property of equality because we're not doing something to both sides. We're just distributing on the one side. So not a property of equality. Go ahead and try the rest of this one on your own. So go ahead and pause it, try the rest on your own, and then check with me. So from this step to this step, we notice our 4 has being subtracted from both sides. From this step to this step, we notice our x is being subtracted from both sides. And then our last step, dividing both sides by 3. Okay, most of our geometry proofs, and we will get some that are more challenging than others, but a lot of our geometry proofs may have geometry at the very beginning, but then will turn into algebra. So if we can get these properties clear, whether we're adding to both sides, subtracting from both sides, etc., then we will honestly have the bulk of the proof part in place. It will just be the geometry that we're working on. So speaking of which, a lot of times the very first step in a proof is setting up an equation, just like we did in Unit 1, using geometry. So for those, I would be setting up the equation on the left, but then on the right, my reason is going to be a definition, postulate, or theorem that allows me to set it up that way. So for example, if they tell me angle A and angle B are supplementary, my first step, that part on the left, I might say A plus B equals 180. My reason on the right has to be connected to why I was allowed to say that. So my reason on the right would say definition of supplementary. The reason that I'm allowed to say A plus B equals 180 is not because they told me it equaled 180, it's because they told me it was supplementary, and I knew that meant that their sum was 180. Okay, so all of these, a definition, postulate, or theorem. So far, most of ours are definitions other than the segment addition postulate and angle addition postulate. Okay, so number 6, we'll just go down the line here. If line M and line P are perpendicular, then angle 1 is a right angle. Okay, so if we're saying angle 1 is a right angle as our first step, the reason we know that is the definition of perpendicular. For number 7, we're given this picture, so sometimes you're given as a picture, and from this we know that angle ABC plus angle CBD equals angle ABD. So the reason we know this equation from the picture is because of the angle addition postulate. So I told you the angle addition postulate and the segment addition postulate from Unit 1 are important for us to know by name. So we needed to know that that was the angle addition postulate. Okay, let's go over to number 10. So given that angle A plus angle B equals 30 and angle A equals 10, then we know 10 plus angle B equals 30. So this would be our first statement. What is the reason that we know 10 plus B equals 30? I hope you said it there. It is the substitution property of equality. Because we stated that angle A equaled 10, we're allowed to replace it in any equation. 11, we have another picture as our given, and then from the picture we decide angle 1 plus angle 2 equals 180. What is the reason that we know that? For this one, I would let you use definition of linear pair, or I would also accept definition of supplementary. That's fine. For number 12, if B is between A and C, and you might need to draw it so that we see B being between A and C, what that looks like, then AB plus BC equals AC. Why do we know that statement? Because of the segment addition postulate. Okay, so the 4 at the bottom, I want you to go ahead and try on your own. See if you're kind of getting the hang of this. Your homework for today is not going to include the geometry ones. It's just going to be identifying the different properties and a few algebraic proofs. So if you're not catching this, it'll be okay, but we do need to start practicing those reasons. So pause this, try 8, 9, 13, and 14. So on number 8, we're given that QW bisects RP at M. So we might want to see what that looks like. Our QW bisects RP at M. Because it bisects, I do know that RM is congruent to MP, equal to it. And I want to use the words that they said. So instead of using like definition of midpoint, I will use the word that they used and say definition of bisect. So if you said midpoint, you're very close, but we just want to use the word that they used. For number 9, based on the picture, T is the midpoint of RQ. For this one, it's a little swapped. So we're looking at this picture, seeing that those pieces are congruent, and that's how we know it's the midpoint. Even though this is our conclusion, we use the definition of midpoint to get there. The reason that we knew T was a midpoint was because the definition of midpoint tells us if these two pieces are congruent, T has to be in the middle. For 13, based on our picture, angle RST equals 180. This one's kind of different. The reason we know that is just by the definition of straight angle. Because it was a straight angle, we knew it was 180 degrees. And then our last one, if AC is equal to BD, we know that AC, these should have lines above them, segment AC is congruent to segment BD. The reason I know if they're equal, then they're congruent, is by the definition of congruent, which says if their lengths are equal, then the segments themselves are congruent. Okay, so that's it for today. You have a few problems to work through, but make sure that you're in that Google Meet and asking me questions if we had questions on this. Again, that backside we're going to get a lot more practice with, so if you're struggling with that, that's okay, but I do want you to start thinking about those reasons, because that's half the battle with Unit 1, is knowing why you're setting up equations that you were setting up. But anywho, enjoy the rest of your weekend. Make sure that you're trying those problems there at the end, and hopefully I'll see you in the Google Meet.